Hello, this is Mahendra Didia. In this portion of the book on liquid formulation, we cover emulsion formulations. In this particular section of the book, there are four modules. They built on the information from Module 2 and Module 4 on physicochemical characterization of solution and emulsion. The subject matter based sequence is used in the book for each category of liquid formulations, including emulsions. These include preformulation, formulation and composition, manufacturing equipment and processes, finally quality and clinical study formulation. Each of these chapters have submodules. In preformulation, we define micelles, oil and water and oil, and double emulsions. We looked on HLB, followed by viscosity, rheology, and sensory attributes, phase separation stability, in vitro release, and bioavailability. We focus on siloxane, also called silicone oil-like physical properties. In formulation and composition, we look at dispersed phase, continuous phase, and emulsifiers, auxiliary agents, formulation composition, double emulsion, and siloxane-based formulation. In this particular submodules, we have also included laboratory manufacturing. Module 15 focuses on equipment and commercial batch manufacturing. And finally, Module 16 contains quality by design and formulation and clinical studies. Readers are requested to review Module 2 and 4, Physicochemical Characterization of Solution and Emulsion. Preformulation includes categories of emulsion and phase diagram in this module. Let's look at preformulation studies conducted in emulsion. Preformulation laboratory studies generate physicochemical information for development of effective and stable dosage form before we initiate formulation development. Preformulation studies for emulsion, functional characteristics of dispersed phase, vehicle phase, and emulsifiers/surfactant. We'll also look at phase diagram of emulsion and immiscible phases in this particular submodule. In subsequent submodules, we will look at other preformulation studies. Emulsion is a biphasic liquid that contains dispersed phase in the form of small globule of liquid distributed throughout the vehicle. The dispersed phase is immiscible in the vehicle. About 80% of cosmetic products, such as gels, creams, lotions, foundation, contain emulsion. Pharmaceutical emulsion may contain FDA-approved instructions. Here is an example of it.
Head lice are a year-round problem. FDA-approved treatments for head lice include both over-the-counter and prescription drugs. They come in shampoos, creams, and lotions. Read the label carefully to be sure a product is safe.
Now let's refresh what is an emulsion. Oil and water do not mix. If you try to mix it, it will form emulsion, that is globules, and these globules will separate. In order to stabilize it, we need to add emulsifier. Emulsifier has hydrophilic group and lyophilic group. Hydrophilic group attracts towards aqueous phase, whereas lyophilic attracts towards the oil phase. And that's the mechanism for stabilization of emulsion. Emulsion categories. Typical emulsion contains a polar phase, aqueous phase, for example, water, relatively immiscible nonpolar phase such as oil or siloxanes, and emulsifier. There are four major categories of emulsions. Water and oil. Water globules are dispersed in oil. Oil and water. Oil globules are dispersed in water. Double emulsion. Oil/water globules are dispersed in oil. So this is emulsion of an emulsion. It can be also oil and water globules, that is oil and water primary emulsion dispersed into a siloxane continuous phase. Double emulsion can also be water and oil globules dispersed into water phase. Reader is requested to review Module 4.2 on classification and type of emulsion for additional information. Let's look at micelles. Micelles also consist of immiscible water or aqueous phase and oil and a surfactant. Surfactant in this case is not charged. That is, it is non-ionic. It has both hydrophilic and lyophilic nonpolar regions. Let's look at here emulsion versus micelle. Surfactants are shown here. Micelle here has a surfactant and a drug is trapped here. It does not have a oil interface. In this case, oil-water emulsion. Whereas in emulsion, there would be an oil droplet, surfactants are attached to it, they form a film, and therefore stabilize emulsions. Micelles are biphasic, has emulsifier, insoluble material in the center, and aqueous phase. Their behavior from physicochemical perspective is similar to solution. Phase diagram. Emulsions contain three components: oil, water, and emulsifier. Emulsifier is soluble in both oil and water. Oil and water are insoluble. Preformulation laboratory studies can be conducted with oil, emulsifier, and water to determine where there would be a clear phase separation and where it would be a single phase of emulsion. Phase diagrams are simple to construct and show you how it's done. We'll take a simple example: acetic acid, water, and isopropyl ether. Isopropyl ether and water do not mix. Acetic acid mixes in both water and isopropyl ether. We look at equilibrium solubility of acetic acid in water and isopropyl ether mixtures. We know that isopropyl ether and water won't mix, so there would be a layer of isopropyl ether and water. We can analyze the amount of acetic acid in the water layer and correspondingly of isopropyl ether. The data is shown here. Water layer, percent weight, water layer goes 37%, and acetic acid concentration increases from 0.69 to 46. Rest of the percent is isopropyl ether. Similarly, in isopropyl ether layer, we can look at it from 100 to 48.7%. We can determine acetic acid, and rest of the material is water. We can create a phase diagram. Let's look at it. So we can draw a triangle, and right angle triangle is easy to draw. In this case, water and acetic acid concentration, and we can graph that. And the graph is shown here. Water, percent water, and correspondingly acetic acid. You can see that when we have 98.1% water, very small amount of acetic acid is there. We do similar. We know the water content and acetic acid content. And the graph is shown here. So now we have a phase diagram. Here's a phase diagram. In this portion, there are two phases, IPE and water. Above this is a single phase. In order to complete the phase diagram, we need to draw a line from apex here. And now you have a phase diagram showing acetic acid, water, and isopropanol. We know this is a single phase here where all three components are miscible. This phase here has immiscible liquids. In emulsion, traditionally, you'll see surfactant listed on top or emulsifier on top. This is 100% surfactant apex. Water, this is 100% water. And oil, 100% oil. This particular red line here is where oil and water are not miscible. Clearly, you can see two phases. M phase is defined as a pseudo single phase, micelle formulation, or homogeneous emulsion phase. In the phase here, we have emulsion. Here we have oil and water separation. Let's look at an example of a pharmaceutical emulsion. Cyclopyrox is an antifungal drug, and it does not penetrate very well from a solution dosage form in the nail. The drug is used for nail fungus treatment. Oil phase here is Campimol PGA, water, and surfactant is a mixture of chromophore and transcriptol P. Ratios of surfactants are shown here: 1 to 1, 1 to 2, 1 to 3, 2 to 1, and 3 to 1. And phase diagram mixing oil, water, and surfactant in different concentrations for each of these mix. And phase diagram shows immiscible phase, clear separation of oil and water, whereas microemulsion formulation in this particular phase 4. As the ratio changes, microemulsion zone changes. For ratio 1 to 3, microemulsion zone is different than for mix 1 to 1. So based on this type of information, formulation scientists can then select the concentrations of surfactant, water, and oil for formulation development.